Standard Deviants present The Dangerous World of Precalculus.
Hi, I'm Galila Azarez, and welcome to the Dangerous World of Precalculus, Part 1. I hope that opening chase scene really got your adrenaline pumping, because the next 2 hours are going to expand your precalculus and algebra comprehension exponentially. We'll review the basics of polynomials, tell you all about rational functions, assess asymptotes, and solve systems of equations and inequalities. For each concept, we'll show you plenty of examples, and when we're through, you'll have enough cool math weapons in your arsenal to face any dangerous precalculus situation with deadly confidence.
And now, it's disclaimer time! To truly absorb the intricacies of precalculus, you must attend your classes, read your textbooks, and listen to your professors! So go to class!
Ahem. While we are running disclaimers, I would like to add that although the standard deviants do not take themselves very seriously, they take their academics extremely seriously. Okay? So you can rest assured that the information presented herein is PhD endorsed.
One last thing. This Precalculus Part 1 video assumes that you know the information presented in College Algebra Parts 1 and 2, including basic algebraic tools and concepts like functions, graphs, and other features of polynomial expressions. You should also know how to put linear and quadratic equations in standard form, multiply binomials, and how to factor these expressions and graph them on the coordinate plane. Not that we want you to buy our Standard Deviants College Algebra tapes for a review or anything like that.
Precalculus is great. Precalculus is the best. If I keep watching this tape, I'm sure to get an A in my test. I said an A, and precalculus is great. I'm getting an A. What a sweet day when I come home with an A. I said
Part 1, Rational Functions.
Section A, Review of Functions and Polynomials.
It's review time.
Hey, folks.
If you don't want to see the review section, just fast forward till you see this ninja. That's the beginning of the next section.
Okay, time to buckle down. You remember the idea of an algebraic function. A variable appears by itself on one side of an equation with one or more other variables on the other side. Like y equals 4x minus 1 and z equals 3x plus 5y. Whenever you see an equation like this, we say that the solo variable is a function of whatever variables appear on the other side of the equation. So when y equals 4x minus 1, y is a function of x.
As soon as we know a numerical value for x, we can substitute it into the equation to compute the corresponding value for y. This process is called evaluating the function. It illustrates the general concept of a function, that for each choice of the independent variable x, there is one and only one corresponding value of the dependent variable y. The equation tells us exactly how to determine that y value. In the case of the equation, y equals 4 times x minus 1, if x equals 3, then y equals 4 times 3 minus 1, or 12 minus 1, 11.
Sometimes, to emphasize the fact that you're dealing with a function, the letter y is replaced by f of x, shorthand for a function of x. So the equations y equals 4x minus 1 and f of x equals 4x minus 1 are really interchangeable in most cases. Also, any other letter can be used in place of f. For example, you could see the equation y equals 3x squared minus 7 expressed as g of x equals 3x squared minus 7.
There are different kinds of functions, grouped into various categories. One main category is polynomials.
Polynomials? Shove that cracker up your...
Polynomials are functions that can be expressed as combinations of coefficients, variables, and exponents. Some examples of polynomials are 5x squared, 4x cubed minus 6x plus 5, and x to the 11th power minus 3.4x squared plus 1/2. Remember, the coefficients are constants, or any real numbers. The variables are letters, and the exponents have to be whole numbers.
One way to think about polynomials is this. Given a value for x, you should be able to figure y using only addition, subtraction, and multiplication. If there is division anywhere in the calculation, it only involves fractional constants that are coefficients, like 1/2. So it should be no surprise that polynomials can be added, subtracted, and multiplied. And the result is always another polynomial. These results can be put into standard forms, graphed, evaluated, and generally manipulated. You should be pretty up to speed on those operations from College Algebra Parts 1 and 2. But if you're still a little hazy, it's not too late to pick up those first 2 tapes for a little review.
You're late, Radical 49. As usual. Seems we have a situation that you must investigate. We have only 2 leads. First, I want you to listen to this phone conversation that we intercepted last night.
Algebra. Asim. Evil plan. No way. Domination. Instant breakfast.
Only other lead is this photo. Study that, so that you'll recognize it immediately.
I'll do what I must.
Do you have any questions?
Actually, yes.
Splendid! Here's Ampersand with some secret agent gadgets that will help you on your assignment.
Hello, Radical 49. This bag contains everything you should need.
Ah, thanks, but I can't even draw a circle with one of these.
No! It's a communicator. It is your direct link with headquarters. Look. No! Don't shake it. You'll lose your image.
How interesting. When do I leave?
Straight away. We need this taken care of as soon as possible.
Section B. Rational functions.
As we mentioned, polynomials make up just one category of functions. Now we are going to look at a different category in which you create functions by dividing 2 polynomials.
Dividing 2 polynomials.
Now, you may remember from arithmetic in grade school.
Now class, there are several ways to writing division of whole numbers.
For instance, if you are dividing 21 by 7, you can either write it as 21 divided by 7, 7 into 21, or as a fraction, 21 over 7. This way of writing division is also called a ratio, which is why numbers written as fractions are called rational numbers. Jimmy, what did I tell you about chewing gum in class? Now take that gum out and put it on your nose!
Polynomials basically behave the same way as those grade school fractions. When you divide two polynomial expressions, you write them like a fraction or a ratio. These functions are called rational functions, and they look like this. But more often you'll see them like this.
X squared minus 5x minus 6 over 4x minus 1. To emphasize that this is a function, we need only to put it into standard form by setting it equal to f of x. Some other rational functions are g of x equals x plus 2 over x minus 1, and h of x equals 2x squared plus 5x plus 10 over x squared plus 4x minus 2. Like with numerical fractions, the top of a ratio of polynomials is called the numerator, and the bottom is called the denominator.
I'm the numerator.
I'm the denominator.
And I'm the terminator.
I'll be above.
I'll be below.
And I'll be back.
The standard formula for rational functions looks like this. F of x equals h of x over g of x. It looks spooky, I know, but it's not. H of x and g of x are just basically code for a polynomial function and another polynomial function.
But rational functions don't always appear in this standard form. Sometimes they come up in an algebra problem in disguise. Your tip-off is that if you see a variable in the denominator, you must know that most likely you're dealing with a rational function. Like this example. The x and y in the denominators tell you these are rational functions.
In your pre-calculus studies, you'll be asked to solve rational function equations and often multiply, divide, add, or subtract them from each other. But how do you do it? Simplify. I pity the fool who must simplify rational functions.
Don't worry, neighbors. I'll help you. We'll start by looking at multiplication and division, because multiplication and division are easier. Thanks for being here with me today. Now please excuse me for just a moment. I have to go place a bet on a monster truck rally.
Section C. Multiplying and dividing rational functions.
You can operate on rational functions just the way you can on any other ratio or fraction. And multiplying two rational functions works the same as multiplying two fractions. Remember how to do that? Right. Just multiply across. You do the same thing with rational functions. Of course, the tops and bottoms of rational functions are polynomials. So to multiply them, you have to use FOIL.
You mean I must foil an evil plan for world domination?
No.
Class, when you multiply polynomials, you multiply in terms of which order?
First, outer, inner, last.
Very, very nice. You all get A's. Except for you, Jimmy. Now stop eating everyone's paste.
For example, multiplying the functions x plus 1 over x plus 3 and 2x plus 3 over x minus 2, we get 2x squared plus 5x plus 3 over x squared plus x minus 6.
Hey, slow down!
Well, although foiling gives you the standard form for a rational function, it is often easier to simplify if you leave the function in factored form. In fact, sometimes the top and bottom start out in a form that can be factored. Give us an example, deviants.
Multiply x squared minus 4 over x minus 3 by x squared minus 4x plus 3 over x squared minus 2x. But before doing the multiplication, factor all of the tops and bottoms of the fractions. You see that some factors, like x minus 3 and x minus 2, end up on both the top and bottom of the fraction. This means you can simplify them by canceling them, like reducing to lowest terms. For a final answer, you can either leave it in factored form or put it in standard form, x squared plus x minus 2 over x.
Which I can assure you is considerably simpler than multiplying the whole business out. To summarize, it is easier to multiply two rational expressions if each expression is factored as far as possible in the first place. Next issue, division.
Dividing two rational functions also works the same as dividing two rational numbers. You know that to divide is just to multiply by the inverse, aka the reciprocal. This whole process is also known by the rule invert and multiply.
Invert and multiply.
Invert and multiply.
When dividing fractions, I bid ye, go forth, invert, and multiply.
For example, dividing x plus 1 over x plus 3 by 2x plus 3 over x minus 2 is the same as multiplying x plus 1 over x plus 3 by x minus 2 over 2x plus 3, which is the reciprocal of 2x plus 3 over x minus 2. So dividing x plus 1 over x plus 3 by 2x plus 3 over x minus 2 gives us x squared minus x minus 2 over 2x squared plus 9x plus 9.
You'll also have to be able to recognize the division operation when it looks like this, a compound fraction. That means the problem we just worked could look like this compound fraction, x plus 1 over x plus 3 over 2x plus 3 over x minus 2. So easy, of course. Anytime you see a compound fraction like this, just remember that it's a division. The fraction on top is being divided by the fraction on the bottom. So you can just put the expressions beside each other to get the more familiar form, then invert the second term and multiply it out to get the answer. Exactly like we just did. Remember, when your function reaches division junction, don't hesitate to reciprocate.
That pretty much covers multiplication and division. Pretty easy, huh? Now comes the tricky stuff. Let's add and subtract.
Section D, adding and subtracting rational functions.
When adding and subtracting two rational functions, you must have a common denominator. Just like when adding or subtracting fractions. Remember that from grade school?
Okay, class, let's find a common denominator so we can add 3/5 and 4/7. The common denominator is 35. And our answer is 41/35, or 1 6/35. Okay, class? Jimmy, stop that nosebleed!
Hope you enjoyed that trip down memory lane. Now let's add two rational functions. Here we've got x plus 1 over x plus 3 and 2x plus 3 over x minus 2. Before you can add these, first you have to find a common denominator. Usually it will be the product of the denominators of the two ratios you are trying to add. So to find the common denominator, you just need to multiply the denominators. After you multiply, the common denominator will be x plus 3 times x minus 2.
Now we have to rewrite each of the original rational functions using the common denominator. You know how changing denominators works for fractions. You can multiply both the top and bottom of a fraction by the same number without changing the actual value of the fraction. You remember this from grade school, too. Class, you know 2/3 is equal to 2/3 times 1, and you know 1 is equal to 4/4. So if you multiply 2/3 by 4/4, you get 8/12, which equals 2/3, only expressed differently. Jimmy, do not electrocute yourself again!
In the same way, you can transform a rational function if you multiply it by an expression equivalent to 1. In this case, we want the new denominator to be x plus 3 times x minus 2. So we have to multiply the first function, x plus 1 over x plus 3, by the denominator of the second function over itself, x minus 2 over x minus 2. The same thing for the second function, multiplied by the denominator of the first function over itself, x plus 3 over x plus 3. Let's look at that again in slow motion. All you're doing is multiplying each part by whichever one of x plus 3 and x minus 2 isn't already in the denominator. Now you have an answer in factored form, but since you want it in standard form, you use the FOIL method to multiply the factors on the top and bottom of each fraction. FOILing gives you x squared minus x minus 2 over x squared plus x minus 6 plus 2x squared plus 9x plus 9 over the same denominator, x squared plus x minus 6. Finally, we can combine the like terms on top, leaving us with 3x squared plus 8x plus 7 over x squared plus x minus 6. And that's your answer.
Hello?
Radical 49!
Double, oh my goodness, is that you? Brilliant disguise.
At sent me with some pertinent information. Ampersand created a new multilingual, multicultural translational device. It deciphers garbled cellular phone messages, but only during the spring equinox. He was able to decipher another key word from the recording.
Tofu! Ah, tofu, so that's the key. But no one eats tofu.
True. Let's mingle.
Okay, quick recap. We started with two rational functions, added them together, and then put the answer into standard form. Fine, but remember the standard form is not necessarily the most useful form. Often it helps to factor both the top and the bottom of the rational function. We won't review factoring here because we know you already know it from college algebra. But keep in mind the common denominator we used above started out in the already factored form x plus 3 times x minus 2, and it's much easier to see simplifications and cancellations when equations are in factored form. So, we can use either x squared plus x minus 6 as the denominator or x plus 3 times x minus 2. Either form is correct.
You already know that the process for subtraction